Hello everybody, I'm Sam Hogarth. Thank you very much for joining us today at NE-RPC. It's really great that in these times of turmoil we can still be a community and meet together virtually while staying safe. So again, thank you very much. Today I'm going to be talking about automated testing, specifically when it doesn't work as promised, when it doesn't deliver what we were told it would, when the tests are getting in the way of us being able to make change, when they're difficult to read, when they're damaging our code base because we've had to add so many layers of indirection that the code itself is now really difficult to work with, that our changes are just taking so long to get done because we can make a really easy production code change, but then we have to spend a couple of days fixing our tests. Whenever we rename a method, a whole load of tests, boom, fail. If you've been around the houses enough, and I've been in this game 10 years now, you will have seen in large code bases, in small code bases, in code bases that are older than you, cases where this happens, because it happens all the time. And it proudly leads towards contrarians being able to say that TDD is dead. It's damaged our code, it's created unmaintainable big balls of mud, and the tests don't even pass for the right reason anyway. I don't think TDD is dead. I think the test first principles are sound, and I think it is still possible, despite those, to be led astray. What I want to do in this talk is kind of refocus our efforts. I want to talk about why that can happen and what that's signaling in your systems and what you can do to prevent that. So I think we should take a deep breath, count to 10, and let's talk about how we can ensure we're testing the right things in the right way. When I write automated tests, I'm doing so because I want to have confidence in what I'm building, and I want to be able to demonstrate that confidence. I want to be able to have confidence later on down the line when I need to make more changes that I am not breaking anything else that I've built beforehand. The only way I can do that in an effective and productive way is if I can get fast feedback. The reason that manual end-to-end tests are discouraged is because the feedback cycles are far too long and the useful information we get out of that is less than you actually think it is. If you consider, for example, a car that's broken down, like it may be obvious to tell that the tyre is flat just by looking at it, but if it's something to do with the engine or one of the other components under the bonnet, you probably can't tell unless you take it apart and figure out for sure. We kind of seem to forget that in software and just focus on end-to-end testing as if it can solve all the problems. But in reality, we need to have faster feedback than that. If I can run specific, targeted, isolated tests in an automated fashion at almost the speed of thought, I can identify changes down to the last edit that I made in the code. And if I can do that, it makes it really easy to fix that issue, because it could just be an undo. It makes it really cheap as well to correct that error. The longer errors remain in our system undiscovered, the more expensive it is to fix them and the higher the impact those errors have when they then manifest. Having fast feedback, having confidence improves the quality of our system, and I'm sure your users will agree. But testing can do so much more than this. You will have no doubt been given requirements by a business owner who hasn't thought through all the use cases or hasn't even thought about the issue at all, to be honest. And exploratory testing is a really interesting way of poking around in that problem space, learning about those edge cases and those boundary conditions and putting some kind of specificity in place to say this is what we should do when this happens. Taking that further, testing in the test first approach, it puts evolutionary pressure on our systems. It pushes us towards really thinking about the design of the system, how we want to use the code. It means that our tests can actually be not just executable specifications, but almost executable documentation of how to use our production code. Now, the purpose of a test is to communicate the intent of the code. It's important to make sure that you're able to clearly communicate that. Like, I'll be flippant. If you can't clearly state what you're trying to achieve, what are you even doing writing a test? It sounds like you need to have a conversation instead. We should communicate the intent of the code by focusing on the behavior and not the implementation. So under the bonnet, we might be representing some data in an array or in a set. That's by the by, to be honest. What we really need to be focusing on is what is the code trying to achieve? What effects is it having? And if we can write our tests towards that rather than specifically to the internal state that they're holding, we will end up with more maintainable tests. They will be more responsive and adaptable to change. In line with that, what is it then that drives a new test? Well, it's a requirement. That might be one given to you by the business, but it might be one that's proved out through experimentation and exploration. Regardless of how you write the test, it needs to be deterministic. It needs to be able to fail repeatedly for the same reasons. If it doesn't do that, if it's susceptible to timing issues, if it's susceptible to the network going down or the database being set up in a particular state, then people are just going to ignore the test and mark it as flaky. It's not going to provide you a useful signal. I think it's worth actually spending a lot of time focusing on how you name your tests. Like I said, tests need to clearly communicate the intent of the code. So this is a pseudo-ish anonymized test from something I've worked with in the past. The test says it should pass the element as the first argument to a function called validate element. Okay, fine. This is quite tightly coupled to a specific implementation. I can tell you this was written after the fact, because you wouldn't think about writing a test this way if you were writing the test first. So this has been written after the fact, and that's fine because the code was there before, written by somebody else before the person who was testing it even came about. So they were using this as a way of poking about understanding how things currently are. It doesn't effectively communicate the intent. It's in there. It's a bit difficult to eke out though. Pass the element to validate element. So what we need to do is we need to find a way to rewrite this. The first thing I like to do is make it in the present tense and make the test name more direct. So one of the things, especially as a British person, is I understand the passivity that comes with the word should. It is very, very wishy-washy. It doesn't mean must. There is an RFC about this. Should means there are valid circumstances where this condition may not hold true. So if this test is actually saying, well, sometimes we'll pass the element as the first argument, but sometimes we don't have to, that's not what was meant. And I kind of know that, right? But I feel like we're just wasting 7 characters and allowing pedants to be pedantic. So let's remove should. Let's write this in the present tense and in a more direct manner. The test is that it validates the element. And now we're communicating the intent. We're performing validation. Let's take a more complicated example to show that this isn't just noddy. So again, this is a real test. It's pseudo-anonymized. The test is saying it should return a map with a key which returns true when all the related elements have empty strings as values. You got any clue what this is doing? I don't. Now, I've been able to look at the underlying code that this is testing. You haven't. And from that, I could work out that it was taking 3 text fields, one for day, one for month, one for year, and it was then reading all of these values and trying to build a formatted date string from that. Are you any clearer from the test that it was doing that? What this is actually testing here is the degenerate case. So when you've got nothing in those fields, you can't format a date object. The particular implementation here, I admit, is quite wonky, but it's because they were using a third-party library and it expected things to be passed in a certain way, right? All that, again, is under the bonnet stuff, right? So let's do the same thing. Let's get rid of should. Let's write it to communicate the intent. Let's make it present tense. Let's make it more direct. What is it doing? It's an empty string when there's no data format. When you get good at this, you can then start thinking about how to structure these tests and how you can think about subcases and different conditions and all that kind of stuff. And here's a trick I like to use. Unfortunately, Java doesn't support this very well with nested classes. C# and JavaScript are really good at it, so I'm going to give a JavaScript example with the Jest testing framework. I'm using describe blocks as a way of identifying, firstly, the overall case under test, which is looking up an address, but then using inner describes as a way of kind of identifying sub pieces of behavior. So when we're looking up an address, we can provide a valid postcode in an input box, or we can provide some junk. We're just focusing, just for screen space here, on a valid postcode case. What will then happen is a search button appears, so we've got a test for that. And then when you click on the button, we can search for that postcode in our database, and we're either going to find it or we're not. If we find it, then what we'll get is a little selection box, so you can choose your house number for the corresponding street. And when you choose an address, it will display an address in a summary panel somewhere. If the postcode's not found in our database, we'll display an error. Again, writing this in this direct way makes these tests really, really specific on behavior rather than on particular implementation. Sure, there are a couple of UI components being mentioned here, like a search button and search results and an address panel and a selector, but those are the behavior as presented, right? These choices need to be made by the user. If we remove all of the JavaScript cruft, all the boilerplate, and just focus on the actual structure, this reads like a good old-fashioned spec sheet. And it reads almost from the kind of writing style that you'll see in newspapers, where you have a headline. We're looking up an address, and then as you go in and in the pyramid structure, you get more and more detail. And that's really, really nice, really useful. If you have one of these tests that fail, it's really clear what's gone wrong. In this particular case, when an address is selected, we're not displaying it in the summary panel. Some behavior in the system has been violated. Remember, the whole point of a test is to fail. It is there to signal to you that something has gone wrong. It needs to be really specific as to what has gone wrong, so that potentially months down the line, this can be corrected without having to understand everything around it. So the way that we drive these tests is through the red-green refactor loop, and I imagine this has been drilled into your head by several TDD advocates throughout the years. But let's do it again. So the first thing we do is we have a red test, a failing test. It's important to make sure this fails for the right reasons. You don't want to introduce any false positives or false negatives in the system. You want a clear signal that the behavior you're asking for has not been implemented. And that will mean getting error messages correct and making them helpful and all that kind of stuff. Once you're happy the test is failing for a good enough reason, you then make it work. Some people who are considerably better at coding than me can probably jump to an absolutely fantastic solution in one go. I like to just bodge whatever I can into place, take whatever shortcuts I need, do whatever hacks I need to do to get that test to green. Because for me, having something that works is better than having something that's elegant but doesn't work yet. And once we get the test passing, and it's passing for the right reason, because we checked it failed for the right reasons, then we have a save point and we can start doing refactoring work. Refactoring is where we eliminate duplication. It's where we do design. It's where we really think about how we want to structure the code and what changes we want to make. Now remember, a refactoring is a change to the structure of the code that does not alter its behavior. And the only way we know that that is possible is if we have a test that can fail if we go too far. And the useful thing about having a passing test is it gives us that save point. So if we do step too far, we can go back to the save point and get working functionality again. Some people like to advocate for your first test being a failing acceptance test. This is described at a really high system level, and it provides a guide. So this is called double loop TDD. The idea is you write this overall guiding acceptance test, and then in order to make that pass, you're probably going to have to go through several of the inner TDD loops, several red-green refactors, but eventually you'll get your test, your acceptance test to green. Now, what I do want to say is the refactor step definitely applies to tests as well, not just your production code. Because tests are effectively executable specifications of how to use your software, they need to be readable, they need to be maintained, and they should be maintained to the same quality as your production code. Because, like I said, when you have a failing case, that may be months down the line, and you want to be able to understand very quickly what you need to do to fix it. One of the problems I see is in the definition of what is a unit test. Kent Beck originally called them programmer tests. A lot of tutorials will use the notion of a class or a function or a method on a class as a way of saying this is your unit that you should be testing. I think if we just naively follow that, every public method has at least one unit test, every class has at least one unit test, we can end up sometimes having too narrow of a definition of what a unit is, and that can make code hard to change because you'll just end up with loads and loads of test failures. I think we should take a step back and think about what a unit actually is. It's a behavior of the system. It's a unit of work. Now, sometimes that unit of work might be bigger than what you're comfortable with. It might be a class or a method, sure, but it might also be a class that uses some collaborators. That's fine. Accept it. As long as you have isolation, as long as you can have that test work in a repeatable way, and you have a reasonable scope of behavior, and you're testing at a reasonable level of abstraction, that's fine. In fact, that might be encouraged because it means your test is probably a bit more adaptive to change. If you decide rather than using collaborators, you're going to in-house everything into the object, the overall behavior of that component of the system is still working. So that's useful. The way that we provide isolation is through a technique called test doubles. And there are various test doubles that we know of that provide different kind of usages, different contexts. So let's go through them. A simple one is a fake, and this is an alternative implementation we use for convenience in the tests. If you're using a MySQL or a Postgres database, you don't want your tests to be too coupled to that, so you could just fake them out with a H2 in-memory database, and that would be good enough. Stubs are fakes that have pre-programmed results, so they're useful for kind of recalling certain pieces of data. If a stub could, for example, be asked to give me customer number 3 and provide a pre-canned, pre-configured customer that you can then test with. Spies are stubs that are a bit more intelligent. They're able to record the usage information. They know who called the methods, what parameters they passed in, how many times methods were called, and then expose that information so you can make assertions on them. Mocks take that one step further. With spies, they just record all that behavior, and you don't have to test the recorded information. Mocks are specifically set up to say, I'm expecting these functions, these methods to be called in this particular way, and verifying that those expectations were met by the code under test is the assertion of the test, is the purpose of the test. Mocks are often misused, so I think I'll be spending a bit of time later on talking about effective mocking. Let's kind of jump back to the assertions in a test though. So classically, and we call this the classical approach, we think of objects containing state and functions having return values. So we will take the bit of the application we're wanting to test, and we'll treat it as a black box. So if it's using dependencies, providing those dependencies aren't too big of a pain in the arse to work with, we will allow those dependencies to be used. If it's touching a database, if we can't have that isolation, if we can't make them repeatable, we may plumb in a test double, and that's fine. But the idea is our assertions are on the state of the object or on the return value of the functions. If you think of a calculator class with an add function, takes two values, sums them, and returns it. Really easy to see how you can write a classical test for that. Really, really easy. But where classical testing falls down is if you're implementing a cache. The whole point of treating an object as a black box is that you shouldn't know whether the cache had to return an in-memory value or whether it had to go somewhere else to compute the value. Testing that in the classical approach is really difficult because you're treating the object as a black box. You're allowing it to use some of its collaborators. So we have the London School, or the mockist approach, which says that rather than thinking about the state of an object, that's the state it holds, we should allow that object to deal with that itself. Because actually state is really coordinating, collaborating objects. So any dependencies of an object under test will be mocked out, and it will have the expected function calls on those mocks set up to be verified. And the behavior of the system is therefore that these mocks are called in a particular way. That's really useful for testing a cache, because if you supply a mock to, for example, get a value from a network, you can, in the case of a cache miss, have a test which says the mock should be called here because the cache is not holding this particular piece of state. The object under test, therefore, is coordinating behavior by calling other objects. And this is actually closer to how object-oriented programming should work. Objects are a graph, they're a web, and they collaborate with each other. The behavior of the application is manifest, is emergent from this web of objects collaborating to create behavior. Objects will have sub-behaviors which can be composed into larger functions of behavior using abstraction. People like to kind of identify as a classicist or a mockist. I prefer to see these as tools on my utility belt. I want to understand what are the appropriate contexts where I pull out a classical approach, or I'd want to test with mocks. And I feel like you should do that too. You should try and keep these at arm's length and know what the right tool is for the right job. A quick word of warning. Tests that have a lot of setup code tend to be bypassing the system in some kind of way. If you're doing database, if your application has a database, for example, it's really, really common to set up the initial state of the application by just yeeting stuff into the database. What you're doing then is you're actually going through the back door to set up your test code. And it's possible if your kind of model layer in the application has a whole lot of complicated business validation rules, that if you're just throwing stuff in the database, you're bypassing all of that, and you can make your code get into states that it's not possible to get into production. And you can end up writing huge amounts of setup code, huge amounts of duplicated code, and huge amounts of tests for stuff that actually you don't need. If you had gone in via the front door, if you need to create some objects, well, create the objects and let them persist themselves into your in-memory database and then use them as the application would use them. You get tests that are more representative of reality. And when it comes to these third-party dependencies, there's a question about whether we should mock them. And if you think about something like a payment provider, you will typically have one business function, which is to make a payment, but your payment provider library will expect 2 or 3 interactions, network calls, to be able to implement that functionality. And that's because there may be challenges or verifications it needs to do. And all that is very, very specific to this particular library. We don't want the concepts of this third-party library to leak too far into our domain code, because it then becomes really tightly coupled. So what I like to do is I like to have an adapter layer which sits on top of this third-party dependency, and it allows us to kind of express what it's doing in business-specific terms, and it allows us to mask any complexity behind that adapter. What we can then do when we need to isolate our model from the third-party dependency is we can stub at our adapter layer. But we still then have to check that we're actually interacting with the real thing correctly, because otherwise we are creating an alternative reality where tests pass but the actual production code can fail. So we will still need to write mocks between our adapter and the third-party dependency. We need to use mocks because we can't control the third-party dependency. That's why end-to-end tests are really brittle, because they're actually trying to execute the third-party behavior. So we need to verify that if we need to call these functions in a specific order, we can use mocks for that. And if we want to verify that we're passing specific data to that dependency, so if it's a REST API call, we need to format messages in a certain way, then we can look at contract testing like packed, for example, as a way of capturing and encoding those expectations. So I think by doing that, just by a bit of refocusing, you're actually quite the way into improving your tests. But the thing is, we still will have fragile tests. And I think we quickly jump to shooting the messenger. We blame testing, we blame TDD when this happens. Why are our tests fragile? Well, it's because testing's fragile, isn't it? No, I actually think your tests in these cases are actually telling you something. If your test code is difficult to work with, and I'm sorry for the bad news, but it's probably because your production code is difficult to work with too. And by and large, tests that have lots of setup and are difficult to understand and are time consuming to work with and are fragile will have specific test cases duplicated across many classes, or have extra hooks, extra bits of supporting code in production just so we test, have a problem fundamentally with encapsulation. Whether that's encapsulation of state, of behavior, of collaborators, or of complexity. And I think it's actually worth, rather than talking about the tests, actually talking about the changes we can make in our production code to better support encapsulation. The first one is leaking state. So it's really common if you're using something like Hibernate or Entity Framework, or if you're using JAX deserialization at the or JSON.NET if you want to convert objects into JSON, for your objects to basically be bags of state, getters and setters. And indeed, there are IDEs which have this as an automatic refactoring. You've got state, but where's the behavior? When you write code that has lots of getters and setters, like I said, there are valid cases where that needs to be because you've got reflection and all that kind of stuff. But when you're writing code that's just got getters and setters, it's got state, the behavior is most likely being implemented somewhere else. And that sounds to me like you're violating the single responsibility principle. What you should be doing is co-locating your state and behavior, because the state is effectively driving the behavior that is being performed. So it is a difficult one because sometimes conventions and frameworks will force you down this route, but actually there are a lot of times where we're just writing getters and setters on state just so that we can test things. We need to find a different way to do that, and I'll come back onto how we can use mocks to do that. But first, another encapsulation leakage comes with how we actually represent data in our system. So primitive obsession is a condition where you have complex domain types. So like a postcode, it has an associated validation, it has a particular structure to it, and you just represent that with a primitive type offered in the system, like string. The problem with doing that is it's too easy, and you can get really far by just representing something in this way. But what you'll find yourself doing it differently as throughout the code is adding lots and lots of tests, and they're duplicated, around the various language properties of your primitive type. Can it be none? Can it be empty? Can it contain weird symbols? Blah, blah, blah. What we should try and do is make these invalid states unrepresentable. And the way we can do that is by using the type system. We can create types to represent domain objects. Now, yeah, under the bonnet, we may still use a string to represent that postcode, and that's fine. But all of the complexity around mapping this domain concept to a string now lives entirely within the postcode object. If it's got to do validation or formatting or anything like that, that behavior can be co-located with that state in that type. What this allows you to then do is make sure that you can't construct a postcode object unless it's valid. That will allow anybody who uses the postcode type to work at a higher level of abstraction. With a decent suite of tests around your postcode type, you can have an increased level of trust that if you're given a postcode object, you can work with it. You don't need to consider the cases where the postcode might be junk or whatever. We are using our type systems as a way of lifting our thinking up a level. The problem is it's really easy to use the type systems in ways to improve testability but actually damage the code. So if we have a typical MVC app which has really big kind of heavy controller and model objects, it's so simple, especially when it's automated in your IDEs, to be able to just say, right, declare an interface for this. We don't really know what it is, we'll just call it controller or iController if you're C#. And the thing is, this at the surface seems solid. The single responsibility, although it's very generic and high level, is that we have a controller. And because we now have an interface for it, we can use dependency injection and we can provide a stubbed implementation of the controller for testing. It seems like it's a good thing to do. But the problem is, this is too broad of a brush. All we've actually done here is increase the cognitive overhead we have in our production code. We now have double the amount of things we need to think about. We've introduced a layer of indirection without abstraction. This is what DHH, the creator of Rails, meant when he said test-induced design damage. What we should instead do is, if we want to introduce a layer of indirection, is we should think about what role that indirection is providing the system. We should think about it in terms of the behavior again. I keep coming to that because it's important. So here we have a role in the system. It's declared as an interface. It's a role interface called message parser. And it's very clear. It has a single responsibility at a given level of abstraction there for parsing messages. There are two implementations here. One is an XML one is a JSON one. We can basically encapsulate the behavior behind the role. What we are trying to achieve here is thinking about how should our software interact with its collaborators. Now, inheritance isn't the only way to achieve this indirection and abstraction. You can do it with composition as well. But what we are effectively trying to do is, like I said, lift up our thinking to deal with things at a different level. There's a piece of advice which is that you should mock roles, not objects. So if we go back to the previous example where we've just lifted a controller and a model interface, it's really easy to mock those, but you will find that mocks are not particularly useful. You probably do end up just testing that these getters are called in this particular way and these setters are called in this particular way, and it's really, really tightly coupled to this exact implementation. Whereas if you're defining things as roles, you're actually thinking about objects as coordinating behavior. And you then think about, well, what behavior do I need my collaborators to provide me in order to do my job? When that doesn't work, when we have code with lots of getters and setters and behavior separate from state, we end up with stuff like this. So this is an example where we have an object who is getting its collaborator and then getting a collaborator of that collaborator and then doing something with it. We call this a train wreck because it's possible for null pointer exceptions in the middle of this chained function calls to completely blow up. But the thing is, if we again see objects as a web of interconnected messages, and that's what a method is, remember, calling a method is passing a message to an object, then this object under test here knows too much about that graph, because not only does it know about its collaborators, but it knows that these collaborators have collaborators themselves, and it knows that those have a particular type of behavior. So not only do objects have an incoming interface, which is their public methods that we want to test around, but we also need to respect that an object will interact with collaborators, and that forms the outgoing interface of an object, and we are remiss to forget that. It's more of a principle than a law, but the idea behind the law of Demeter is that objects shouldn't know too much about the overall graph that they're in. They should know about their collaborators, but nothing anything further than that. The way that they recommend, this is from the Nat Price, Steve Freeman, Growing Object-Oriented Software Guiding by Tests book, the way that they suggest achieving that is through a principle called tell, don't ask. Here's an example of some order processing code. So it's a function, it's given a customer and an item, and the first thing it's doing is it's getting a wallet from a customer, then getting some money out of the wallet, and then it's doing some sums and putting that back into the wallet. It's then going off to the stock list and saying, take this item off the shelves and dispatch it, and then it's increasing our personal balance. This knows too much. It knows that a customer has a wallet, it knows that a wallet has a balance. It's doing the behavior of that wallet, it's doing the sums, and it's then setting it back on it. It's working at too lower level of abstraction, it's too tightly coupled to the details, and this is an absolute pain to test. It's actually not representative of reality either. A shopkeeper doesn't take your wallet out of your pocket, take the money out of the wallet. We need to co-locate the state and the behavior. So along the lines of the tell, don't ask principle, we can work at a higher level of abstraction and simplify this code to this. So processing an order involves telling a customer to pay, telling the stockroom to dispatch the item to the customer, and registering the sale on our account book. Now, that state is still going to be there, but it's now encapsulated. A customer knows it has a wallet, a stockroom knows it has a stock list, an account knows that it needs to do the calculations in a certain way. This is an inherently simpler method, and it allows us to use mocks to verify that the behaviors provided by our collaborators are working as intended. And again, if these collaborators are sufficiently tested themselves, maybe even in the classical approach, if they're doing a lot of state-based stuff, we can build upon that level of trust. But hang on, Sam. Aren't mocks then, if you reduce your code to that, aren't mocks just testing the implementation? To be honest, yeah, it depends. They can do, and some of the mocking frameworks make it really hard if you change method names. They will fail and all this kind of stuff. But I think the reason it depends is on why are you using mocks. If you are mocking objects, which are kind of really complex, have lots of responsibilities, then yeah, you probably are quite tightly coupled to a particular implementation in terms of managing the state and stuff. If you're thinking about it in terms of behaviors, it's still testing an implementation, but it is very subtly at a higher level of abstraction. And I think it's still useful. And to demonstrate that, if we go back to our double loop of TDD, where we write a failing acceptance test, using mocks effectively allows us to write from the outside in and test in that manner. So when we're writing the acceptance test, we'll think, what behavior are we implementing? What behavior do we need collaborators to do in order for me to achieve my goal? And I'll mock those. And then what I'll do is, once I've got my piece of the work under test, the view layer, for example, I can go to my mocks and work backwards and think, what collaborators and what behavior on those collaborators do I need to do my bit of the job? And go back and back and back, and eventually the acceptance test will turn green. You're working outside in, using the mocks as scaffolding. Now, if you choose to throw those away after the fact is entirely up to you. But again, I think this is really useful for making sure you're capturing both the high and the low level details of what's going on. Okay, let's wrap up. There's a lot to chew on there, and if we're going to try and distill it down just in time for close into a few messages, I think it's important that tests need to fail for the right reasons. You want to make sure you're not getting false positives, not getting false negatives in your system. You need meaningful signals of failure. In order to do that, you need to make sure it's your behavior you're testing, the intent of the code, not necessarily the nitty-gritty implementation details. Effective testing of behavior requires you to think about roles in your system, not objects as bags of state. And if you mock along those lines, then you will get composable systems that can be plugged together at different levels of abstraction. But it's really important to not forget tests can be refactored too. Tests need to be maintained at the same level as your production code. And finally, listen to your tests. It's not the test's fault that they're hard to work with. That's it's revealing to you that there's design issues in your production code that can be addressed. Alright, so we're going to be providing the links to the Q&A in the doobly-doos down below, and that way and that way and that way. But I'd love to hear what your thoughts are on this. I hope it's given you sufficient levels of confusion, and I am more than happy to deflect any questions in the Q&A session. So thank you. Bye.